Okay, so yeah, what about one like this? So if we were, when you're setting this up, I just want to go over why this is a little easier than what we did yesterday, because it's giving us specific amounts for the cost per unit area, right? So if we drew this guy, it's got a square base. But the height is not necessarily the same dimension. So the base dimensions would be x by x, but we could call the height y. See what I'm saying? And so then when you're adding up the total cost of building this thing, like what are you going to do? You know, like what are you going to multiply? You're going to have the areas of each side, right? What are you going to multiply the area of the top by? By 6, yeah, right. To get the cost of the top, you multiply the area of the top by the constant 6. What do you get to get the cost of each of the 4 lateral sides? Yeah, you're just going to multiply by 4, right? Right. So you're going to get 4 times x times y, and then you're going to get 4 of those. And then the floor, you're going to multiply by, by 4. Yeah, 4.5 was the sides, wasn't it? Yeah, right. Make sense? And so you get an easier cost function. You don't have to deal with the Ks and like yesterday we had K and 7K because they never told us what the cost per unit area was for any of this stuff. But we just knew the ratio of between the dome and the barrel, right? Okay. All right. And on the assignment then.
Is this one of the questions?
What's that?
Is this one of the questions on the test? Or?
That's one of the questions on the test.
Wow.
Yeah. Okay. Which assignment was that on? Do you remember?
It was like
Practice 1. Okay.
it was question 4. So you can't complain. I can't even make it past. I can do the 1 + 1. Except for one time I did a 0. Oh gee, let's still hold it up. I wonder if I'm gonna finish that. What? The cards.
Okay, yeah, so see what your question is here. So this isn't a hard one to deal with. This is when you cut corners out and fold up the sides to turn a sheet of cardboard into an open box. Right, we did one of these in class, and no, that's as much as I'm doing. You guys got to do the rest. So one like this. So if it's 31 by 17, it's no big deal. Then you just have 31 minus 2x, right? And so part A. What do you do with part B? Well, they tell you that in part B, they tell you that the side lengths are S. That's all they tell you. It's a square. They don't tell you what they are, but they're just S. So find the volume of the largest box that can be formed in this way. Yeah, so your answer is going to have an S in it, right? Because you don't know what S is. That's a parameter, right? Because it's a constant once you start the problem, but you don't know what the value of S is. It could be 100 or it could be 10 or whatever, right? So you're going to end up with S's in your answer. You'd have to. Okay. So like if we set that up, everybody agree that the box is just going to look like this? There are lots of boxes today. Right? right? So this is gonna be S minus 2, S minus 2, or sorry, minus 2x, right? Because we're cutting the corners are how I'm cutting out x by x slots, right? So those are my dimensions, right? So then the total, we're trying to maximize volume, right? So what's the total volume? Volume is going to equal S minus 2x squared times x, right? So if we square all that out, what do we get? That's going to give us, that, isn't it? Right? That's volume as a function of x. So what would we do? Well, I know what's messing with you guys is that s is in there. S is not a variable. S is a constant.
Do you just do the derivative?
So say it again.
Do the derivative?
Just do the derivative, right, like we normally do. And we didn't even do the domain here, but what would the values of x be? The smallest x could be is 0. The biggest x would be half of s, right? Okay. And so v prime is going to give us what? 12x squared minus 8s. I'll put the s first. X plus s squared, right? That's kind of a weird one. But my only variable is s in this case. So does this factor? Maybe, but I would just solve it with quadratic formula, right? So if I want to find out where the derivative is obviously nowhere undefined, where is it 0? So v prime equals 0 when all this is 0, right? When 12x squared minus 8s x plus s squared equals 0. Well, if I just solve that using the quadratic formula, this whole thing right here is a. That's the coefficient of x. That's b. And that's c, right, in the quadratic formula. So I would just get x equals negative b, so that's positive 8s, plus or minus square root b squared is 64s squared minus 4 times a, which is 12, times c, which is s squared, all over 2a, 24. So what's that look like? 8s plus or minus the square root of 64s squared minus 48s squared. Well, that's 16s squared. What's the square root of 16s squared? 4s, right? See what I'm saying? Okay, so we're going to get 8s plus or minus 4s over 24. Well, that's giving us two solutions then. That's telling us either x equals 12s over 24, which is s over 2, or x equals 4s over 24, which is s over 6, right? Only one of those is an interior critical number. Which one? Because look at our domain, right? Our domain just goes up to s over 2. So that's not a useful critical number because it's an endpoint, right? That makes sense? So we only get one interior critical number. And if we were to use the second derivative test here, we can take a second derivative. What do we get? 24x squared, or sorry, 24x minus 8s. If I plug in s over 6, that gives me a negative second derivative, doesn't it? Right at that critical number? So then that's all we need. If I make my table, on our domain from 0 to s over 2, we get one interior critical number at s over 6, which is a 0 of the first derivative, get a negative second derivative, so that's a maximum. If I only have one interior maximum and the function's continuous, that's the maximum. Okay. So regardless of what s is, we know that it's whatever 1/6 of s is going to give us maximum volume. Okay? Good? All right. Okay, what about one like this? This is another useful one for the test. There's something like this on the test. This would be a good example. So a rectangle is constructed with its base on the diameter of a semicircle with radius 18 and with its two other vertices on the semicircle, right? So then what would be a useful radius to draw here? The radius of the semicircle is 18. I could draw it anywhere, but like this wouldn't be a very useful place for me to draw my radius if I just drew it right here along the base. I could do it along the base. Straight up wouldn't be the best either.
Maybe to the vertice.
To the vertex. Yeah, that would be a good one. Okay, how come? Here's why. Let's talk about this. There's a couple things you can do here that are useful. So that's 18. That's useful because look what it does. It gives us a right triangle. And it gives us a right triangle where one of the dimensions is the height of the rectangle, right? So that's good. We're connecting the radius to the height. Okay, another thing that's very useful to do here is, and you have the freedom to do this in math, right? It doesn't say anything about putting this in a coordinate plane or anything like that, right? But it's useful to do that. It's useful to orient this in the XY plane in the most convenient way. There's nothing stopping us from doing that. So let's do it. If we where should I put the origin in this problem? Where's that? Describe that. Where does that go? Where should the origin go?
Right above where it says.
Okay, so right there, right? Yeah, that makes sense. So we would let this be the x-axis, and we would let this be the y-axis. And then that's pretty convenient, isn't it? That's a pretty convenient place for us to put this semicircle. Okay, if we do that, then what would the coordinates of this point be right here? Okay, yeah. Well, okay, so if x this is sort of inconvenient. The fact that they told us they used x as the distance. I wouldn't do that. I wouldn't call that x personally. Well, I'd let x be something different. In fact, let's change that. It'll work, but there's probably a better way to do this. Couldn't we let x equal that distance? And then that becomes the x coordinate of that point. The y coordinate of that point is just y, where y is the height of that rectangle then. Everybody see that? Okay. So the width of the whole red rectangle then is actually 2x. Right? Okay, so what are we trying to do? We're trying to maximize area. Well, the area of the rectangle is just what then?
2xy.
2xy, exactly, right? The width, which is 2x, times the height, which is y. So we need an equation of constraint there. Well, what's our constraint? The constraint has to come from the number.
It's the a squared plus b squared.
Exactly, yeah, it's the 18, right? The constraint is the radius of that semicircle, which shows up in this right triangle. See that? Okay. So we just end up then, based on this right triangle, we get x squared plus y squared equals 18 squared. And I would just solve for one of those and plug it into my function, right? Like we could solve for, doesn't make any difference. What if we solve for y? If we solve for y, we would just get y equals square root of 18 squared minus, so was that 324? 324 minus x squared, right? Okay. So if I make that substitution, then I get area as a function of x equals 2x times the square root of 324 minus x squared. Okay, make sense?
Yeah.
And what's my domain gonna be? So now we've got a function of x, so we need to know, we're gonna make a table, well, we have to know the domain, so where we're gonna look for critical numbers. What's the
0.
smallest that x could be?
0.
0, yeah. And you can kind of see what happens if x goes to 0, what's the height gonna go to? You can use that equation right there if you wanted. That relates x and y.
18.
18, right? So when the width is 0, the height is 18, what happens? What's the biggest that x could be? 18, yeah. In which case the height goes to 0. So there's our domain. And now I would just differentiate that thing and make my table and go to town. Okay? An alternate way of doing this, that works fine. We made a right triangle out of this, which I think is always a great way to go. But an alternate way of doing this would have been for us to say, okay, well, once we orient this semicircle so that the center of the circle is on the origin, then can you guys tell me what the equation of a circle is?
Area.
The equation of a circle, not area. I mean the equation of the circle. Do you guys remember this? You must have done this last year, I think, a little bit. Did you guys do analytic geometry where you did circles and, right? You talked about that stuff a little bit. Circles and ellipses and.
Yeah.
Okay. So what's the? Can you guys tell me what the equation of a circle is if the radius is r? And let's say the center of the circle. Did you guys do this?
Yeah.
So if you have a center at
Yeah, H and K.
HK, right? Right. So what would this? And the radius r?
I don't know off the top of my head. Oh, is the radius part of the end? Does it
So r squared is right.
Oh, it is?
Yeah. So you get. So how does that work then?
I don't know. Is it plus or is it minus?
X minus h squared
Plus
y minus k
equals R.
squared equals r squared, right? Well, our center is at 0, 0, so it makes it easy, right? And our radius is 18. So the equation of this circle is, our circle is x squared plus y squared equals 18 squared, right?
What?
That's the equation of our circle, but we only want the top half of that circle, right? That makes sense? So really all we're doing here is we're just solving for y. If I solve for y, I get y equals plus or minus the square root of 18 squared, which is 324, minus x squared. Okay, well, what's that mean? Well, if we were to graph this thing, the math gods are very tricky this way. When we solve for y and we get plus or minuses, the math gods are breaking those up so that each one of those is individually a function. the circle violates the vertical line test, so the circle is a non-function, right? But if we graph these as two pieces, plus the square root of 324 minus x squared, if I graph that, what's it look like? It just looks like, whoops, looks like this. Or minus, well, what's the minus one? I'm just multiplying this whole thing by -1, which just reflects it over the x-axis. Those are the two semicircles I get. So the equation of the semicircle is just the green part, right? Just plus the square root of 324 minus x squared, right? So if that's the equation, we could call that f of x if we wanted. Then any point on that curve is just going to have coordinates x square root of 324 minus x squared. So we could have just done this whole problem just thinking of this as some function, and the height of the function is just y, right? That makes sense? The reason I say that is because on the test, you guys have something similar, right? On the test, you guys have a problem where it looks very similar, only instead of a semicircle, it's a little bit easier. You just have some parabola, and you're trying to find, I think it's a rectangle, the biggest rectangle that fits under the parabola. And so now, again, you'd set it up kind of the same way, right? If this distance is x, and this distance is y, then the coordinates are x, y, but you already know what the secondary equation is. It's just the equation of the parabola. Like maybe the parabola, I don't know what it is, but maybe the equation of the parabola is 4 minus x squared or something. I don't know what it is. But then that's what's telling you the relationship between x and y. Okay? Make sense? Okay, so there's a little helpful hint on that one. Okay. Okay, what about stuff like this? So we didn't really have, maybe we'll come back at the end and look at like some really interesting economics concepts, like the elasticity of demand and some stuff like that, where you can do some cool calculus that people really do. That's, if you're trying to be a quantitative economist. But let's look at some just basic stuff here. So a company manufactures and sells X television sets per month. The monthly cost and the price demand equations are this. Okay, so here's our cost function. Cost as a function of x equals 73,000 plus 60x, where x is the number of television sets per month. Right? We're trying to decide how many to build per month. Try to set the production levels to maximize profit. Okay. Now, what is this price demand equation or price demand function? A lot of times they call it. A lot of times people just call it the demand function. So this, a lot of times people just call that the demand function. So if you look at microeconomics, you guys already know some stuff. Like how are, in a competitive market economy, how are price and demand typically related? Say it again. Right, okay, so as demand goes up, price goes up, right? If there's a scarcity of an item, people typically want it, and then the price goes up, right? So if the demand increases, typically due to scarcity, then price goes up, right? Okay, so they're telling us this is the relationship between the price of each item, the price that we charge and the number that will be purchased. Okay, does that make sense? Okay, so if this is true, if this is the price per item and X is the number of items, then what's the revenue going to be? Revenue means the amount of money coming in, right? Have you guys talked about this ever before? Revenue is the money that a company's making, all the money that's being paid into the company. Costs are the money that's going out, right? There's a cost associated with building something. So what's profit then? Let me write this down. So revenue money coming in. Cost equals money going out. Which one would you prefer is bigger if it's your business? Revenue. Yeah, how come?
Because then you're making money.
Okay, because what's profit?
The difference.
The difference, revenue minus cost, isn't it? Right? So profit P is just revenue minus cost, agree? Okay, so what is the revenue now? So we got to come up with a revenue equation. What's R? The revenue is the amount of money coming in, right? The price that we're charging per item is this function, 300 minus X over 20, okay? And then the number of items is X. In this case, the items are television sets that we're selling. So what's the revenue? In terms of the price per item and the number we sell. Because little p just stands for price per television set. How much money are we making? Again, if the small p, little p, is the price per television set, and X is the number of television sets that we're selling, what's it going to be?
Why don't you multiply them?
You multiply it. Exactly. It's a product of the two, isn't it? The revenue is going to equal X times P. So that's X times the quantity 300 minus X over 20. Make sense? And we know what the cost function is. It's right there. So we can arrive at we can build a a profit function out of this, can't we? Right? If profit is revenue minus cost, then we know P of X is revenue, which we just built, X times the quantity 300 minus X over 20 minus cost, which is, we're already told, cost is 73,000 plus 60X. There's our profit function. What's our domain? What's the smallest number of television sets that we could sell? 0. What's the biggest number that we could sell? Infinity, I guess, right? That's probably not possible, but somewhere in there, we're not going to want to build infinity anyway, because that's not going to, at some point, you could build too many, and that's what this is going to tell us. It's going to tell us what's the optimum amount, okay? And that's a pretty easy problem from there, isn't it? Right, I just distribute the X, collect like terms, build a polynomial, and once you have a polynomial, it's easy. Polynomials are the easiest functions to differentiate, right? Okay, make sense? Okay? So, I kind of want to know how much that is. I kind of want to know. Let's see. So if we put all this together, then we're going to get negative X squared over 20 plus 300X minus 60X. So it's minus 30X minus 73,000. Okay, so there's our profit function. We differentiate once. What do we get here? That's something's goofy there, huh? Oh, you know what I did? No wonder. Yeah, that's 300X minus 60X. Let's say this can't all be negative. So that's 240X. It's positive 240X. See what I'm saying? There we go. Yeah, that makes more sense. One of those terms had to be positive. So now if I differentiate, I'm just going to get 240 minus X over 10. And if I take a second derivative, what's that tell me? What's its sign always going to be? Negative, right? So when is P prime 0? when X equals what? 2,400, yeah.
Yeah.
And we're gonna have a negative second derivative, so it's a SAT function, so that's our maximum for profit, right? So that's the amount of TVs that our company's gonna sell. We're not gonna just get greedy and try to sell too many, because our profit's gonna go down.